Hello, geometry students. Let's take a look at your 8.2 notes. We're going to look at the Pythagorean theorem in more detail than we have before, and you may not know, but the Pythagorean theorem has a converse that we're also going to look at. So let's first of all just restate the Pythagorean theorem, which says the following. The square of the measure of the hypotenuse of a right triangle is equal to the sum of the squares of the measures of the legs. Now, I might say that a little bit different than you're used to saying. In fact, let's take a look at this right triangle that has legs A, B, and hypotenuse C. You're probably used to saying A squared plus B squared equals C squared, and that's perfectly fine. There's nothing wrong with that. But I prefer to turn it around, and I'll tell you why a little bit later. So in our theorem, the Pythagorean theorem would be stated as follows. If triangle ABC is a right triangle with the right angle at C, sorry about the bell, if ABC is a right triangle with a right angle at C, then our conclusion is, and again, I'm going to write this backwards maybe than you're used to seeing it, C squared is equal to A squared plus B squared. Now again, you can certainly turn that around because equality is symmetric. You could write it either way, but there's a reason I like to start with the hypotenuse, and we'll talk about that a little bit later. So now there are many, many ways to prove the Pythagorean theorem. In fact, you're going to be doing a little project that's kind of a visual proof of the Pythagorean theorem. But let's walk through a proof that I really like because it uses some of the information that we've learned recently in class. So let's prove the Pythagorean theorem. So given that ABC is a right triangle with a right angle at C, let's prove that the measure of the hypotenuse squared is equal to the sum of the squares of the measures of the two legs. Okay, so to use that, we're going to use a theorem that we've learned recently in class. So let's start this proof by just stating that we have an altitude. So in case that altitude weren't already there, let's draw segment CD, which is the altitude from C, okay? Now, what justifies that altitudes exist? So here's point C, and then this point D is the point on the opposite side, such that when I draw CD, CD is going to be perpendicular to the opposite side. So that point exists, and so the existence of this segment then is guaranteed by one of our first postulates of the year, which just said anytime we have 2 points, then there exists exactly one line. Exactly one line. Okay, so what we've drawn then is an altitude to the hypotenuse of a right triangle. So this will remind you what we've talked about recently in class. So I want to draw your attention to the legs, the measure of the legs of the triangle, A and B, and recall we learned a theorem called the geometric mean leg theorem that says, let's start with A, that leg A, the measure of leg, the A, which is the measure of the shorter leg, okay, is a geometric mean between the entire hypotenuse, so that entire hypotenuse is represented by C, and the piece of the hypotenuse that A is touching or is adjacent to. So A is the geometric mean between C and Y. So let me complete our proportion here. Also, our other leg, B, it is also a geometric mean. The other leg, the measure of the other leg, is a geometric mean between the entire hypotenuse and the piece that it touches. So we'll write it like this. B is the geometric mean between the entire hypotenuse C and the piece of the hypotenuse that B touches. Okay, so we will justify that with the geometric mean leg theorem that we have discussed recently in class. Okay, so the next thing we're going to do is we're going to cross multiply. So our step 3, we're going to say that when I cross multiply this way, A times A is A squared. And then when I cross multiply the other way, we'll get CY. Okay, let's put a comma, and then let's cross multiply in the other proportion. So we'll say that B squared is equal to C times X. So B squared, oops, wrong pen, just a second. Oops. Hold on. So B squared is equal to C times X. Okay, so we'll justify that. That's just a property of proportions. So we're just going to say if we have a proportion, then we can conclude that the cross products, let me fix that, the cross products are equal. Cross products are equal. Okay, so now what I'm going to do is I'm going to take this first equation and I'm going to use the addition property of equality, and I'm going to add the same amount to both sides. What I'm going to do is I'm going to add b squared to the left side of this equation and cx to the right side of the equation. So if these two things are equal to start with, I can add the same amount to both sides, and the left side will still be equal to the right side. So I'm going to say in step 4, I'm going to say that a squared plus b squared is equal to cy plus cx. So again, I just took b squared and I added it to the left side, and then cx and added it to the right side. This equality means that b squared and cx are the same thing. So if I add b squared to the left and cx to the y, I'm adding the same amount to both sides. So that property then was the addition property of equality. I added the same thing to the both sides, and the left side is still equal to the right side. Okay, the next thing I'm going to do is use a little bit of algebra, and I'm going to notice that these two terms have a common factor of c, so I'm going to factor that out. All right, so in step 5, we're going to say that a squared plus b squared equals c times y plus x. So what we did is we just used substitution, right? I replaced cy plus cx with an expression that it's equal to. So that's using substitution, and I'll just put in parentheses that we use some factoring to do that, okay? And then if you look at the diagram, y plus x can be replaced with c. From our diagram, we can see that c and y plus x are the same thing. So I'm going to rewrite step 6, but where I see that y plus x, I'm going to take it out and replace it with what it's equal to, which is c. All right, so we're going to say that a squared plus b squared equals c times c, or in other words, c squared. So now to finish this proof off, I'm going to do a couple of things. I'm going to first of all I'm going to multiply c times c, which would give me c squared, and I'm also going to turn this statement around so it looks like our proof statement. So we're going to say that c squared is equal to a squared plus b squared. So I did a couple of things. Oh, oops, I forgot my reason for step 6. Step 6, my reason was just substitution. I replaced y plus x with what it's equal to. So 6 was substitution, and then step 7, our reason is the symmetric property of equality, and we also used substitution because I replaced c times c with c squared. Okay, so I like that proof of the Pythagorean theorem. It uses that geometric mean leg theorem that we have used, have learned recently in class. So now let's look at a couple of examples where we apply the Pythagorean theorem. So let's look at example A. Here we have a right triangle with legs 6 and 15 and the hypotenuse x. So we can find the value of x by using the Pythagorean theorem. The Pythagorean theorem tells us that the hypotenuse squared is equal to the sum of the squares of the two legs. So that would be 6 squared plus 15 squared. All right, so x squared then is equal to 36 plus 225. And 36 plus 225 is equal to 261. So now if I'm solving for x and x is being squared, the inverse of squaring x is to take the square root of both sides. So we will take the square root of both sides, okay? And when we do, we're going to get that x is, now let's simplify this radical. And we don't have time to do the arithmetic in this video, but with a little bit of arithmetic, you can find that the greatest factor of 261 that's a perfect square is 9. So we're going to break the square root of 269 up into the square root of 9 times the square root of 29. All right, we pulled this perfect square factor out and we can simplify it. So then our final answer is going to be 3 times the square root of 29. Okay? Let's take a look at letter B. So in letter B, we know the hypotenuse, but we don't know one of the legs, we do know the other leg. So using the Pythagorean, let's just call the, well, never mind, the unknown leg is called x. So using the Pythagorean theorem, we can say that the square of the hypotenuse, let me write that again. Okay, the square of the hypotenuse is equal to the sum of the squares of the two legs. So that would be x squared plus 9 squared. All right, 11 squared is 121. That's equal to x squared plus 81. I'm going to subtract 81 from both sides and get that x squared is equal to 40. Then we will take the square root of both sides, okay? So x, and I'm going to turn it around and write it as x equals, now 40 can be broken down to the square root of 4 times the square root of 10. I pulled 4 out because it's a perfect square factor. It's the biggest perfect square factor of 40. So we pull that out so we can simplify it and get our final answer to be 2 times the square root of 10. Okay, now the next thing we're going to talk about, Pythagorean triples. And this is something that you may have instinctively started to figure out, but if not, it's time to learn some Pythagorean triples. It'll help you so much in the future. So first of all, what is a Pythagorean triple? Well, a Pythagorean triple is a set of 3 non-zero whole numbers, okay, so non-zero whole numbers, such a, b, and c, such that a squared plus b squared equals c squared. So here's some examples, and I'm going to highlight these, and I want you to also start memorizing these Pythagorean triples, okay? And these are just a few of the infinite number of Pythagorean triples for which this would be true, that a squared plus b squared equals c squared. But if you can start memorizing these, they pop up often, it'll help you save some time. So 3, 4, 5 is a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. 5, 12, 13 is another Pythagorean triple because 5 squared plus 12 squared equals 13 squared, and so on. Now, another very interesting thing about Pythagorean triples is that any multiple of a Pythagorean triple is also a Pythagorean triple. So in other words, if I take these three numbers, 3, 4, and 5, if I multiply them all by 2, I'd have 6, 8, and 10. This is also a Pythagorean triple. 6 squared plus 8 squared equals 10 squared. If I take 3, 4, and 5 and multiply them all by 3, I'd have 9, 12, 15, which is another Pythagorean triple. 9 squared plus 12 squared equals 15 squared. So in other words, if I take 3, 4, and 5 and multiply them all by the same number, the resulting three numbers will also be a Pythagorean triple, okay? So that's true of all these. If 5, 12, 13 is a Pythagorean triple, if you multiply them all by 2, then 10, 24, 26 is a Pythagorean triple, and so on, okay? So here's how that can help us. So let's take a look at this example. We're asked to find x in this right triangle. X is the hypotenuse. Now, we could do it the long way. We could go ahead and say that x squared is equal to 48 squared plus 20 squared and do all the arithmetic, or we can be clever and start looking for maybe some hidden Pythagorean triples. So if you look carefully at 48 and 20, I want you to notice that 48 is equal to 4 times 12, and 20 is equal to 4 times 5, and I want you to notice that 5 and 12 are 2/3 of a Pythagorean triple. This one, 5, 12, 13. So if this leg is 4 times 12 and this leg is 4 times 5, then this hypotenuse must be 4 times 13. So if you can find that hidden Pythagorean triple, all you have to do is just a little bit of arithmetic, and our final answer is x is 52. Okay, so again, what I've circled in yellow is a Pythagorean triple. We had 2/3 of the Pythagorean triple. All we had to do is find that missing one and then figure out what their common factor was. Let's try it again. Let's take a look at letter B. So here we have 50 is the hypotenuse, 14 is one of the legs, and x is the other leg. Well, as I look at 14 and 50, I'm kind of thinking about this Pythagorean triple. Oops, I shouldn't have done that. This Pythagorean triple, 7, 24, 25. So notice that 25 is equal to 50 is equal to 25 times 2, and 14 is equal to 7 times 2. So 7 something 25 is a Pythagorean triple, or remember 7, 24, 25 is a Pythagorean triple. So if one of the legs is 7 times 2, then this leg is going to be 2 times 7, then this leg will be 2 times 24. So this is 2 times 24, and so we can get very quickly that x is equal to 48, okay? Again, it's just a matter of finding a hidden Pythagorean triple and noticing that you have a Pythagorean triple that has all been multiplied by the same number. Okay? If you look at this last example, this one's pretty straightforward. We have a right triangle. We need to find the length of the ladder. Okay, we have a right triangle. Well, one leg is 5 and the other leg is 12. That should sound familiar to you. 5, 12, 13 is a Pythagorean triple. So without doing any work, we know that x, the measure of the hypotenuse, is 13. So x is equal to 13. So now let's look at the converse of the Pythagorean theorem. Now the Pythagorean theorem assumes you have a right triangle, so given a right triangle, the conclusion is that the sum of the square of the hypotenuse is equal to the sum of the square of the two legs. Well, let's turn that around and start with this hypothesis. If triangle ABC with given sides A, B, and C where C is the largest. So if I have a triangle ABC with sides A, B, and C where C is the largest side and C squared is equal to A squared plus B squared, then our conclusion is that triangle must be a right triangle. Then triangle ABC is right. Okay, so that's just the converse. The Pythagorean theorem assumes we have a right triangle, and then the conclusion is C squared equals A squared plus B squared. So the converse is, if C squared equals A squared plus B squared, then we can conclude that that triangle must be a right triangle. And then furthermore, we can extend it to some other important information, and that is if I have a triangle ABC where C is the largest side, if the square of the largest side is less than the sum of the squares of the two legs, you're going to know, or the sum of the squares of the two shorter sides, you're going to know that that triangle ABC is an acute triangle. And so I bet you can guess what's happening here. If the square of the biggest side is greater than the sum of the squares of the other two sides, then we can make the conclusion that that triangle ABC, is obtuse. All right, so let's look at some examples. So this example says, determine whether each set of numbers can be the measures of a triangle. If so, classify the triangle as acute, right, or obtuse. So the first part of this, remember, has to do with that triangle inequality theorem that says the sum of the measures of any two sides has to be bigger than the third. So first of all, can 7, 14, 16, we're missing a comma. Why don't you go ahead and add that comma? Sorry about that. Can 7, 14, and 16, can those three measures be the sides of a triangle? Well, what we need to do is check and see that the sum of any two is bigger than the third. So 7 plus 14 is bigger than 16, 14 plus 16 is bigger than 7, and 7 plus 16 is bigger than 14. So yes, it can be a triangle. Now let's determine what kind of triangle it is. So what we're going to do is we're going to take the biggest side and square it and compare that to the sum of the squares of the other two sides. So 16 squared is 256, and 7 squared is 49, and 14 squared is 196. If you add those together, 256, 49 and 196 is 245. Okay, so notice that the biggest side squared is 256. The sum of the squares of the other two sides is 245. So the biggest side squared is larger than the sum of the squares of the other two sides. So we can conclude that this triangle is obtuse. Okay, how about letter B? First of all, can it make a triangle? Well, let's see. 9 plus 40 is bigger than 41. 40 plus 41 is bigger than 9, and 9 plus 41 is bigger than 40. So the sum of any two sides is bigger than the third, so it's definitely a triangle. Now let's find out what kind of triangle it is. So we'll take the largest side and square it, 41 squared, and we'll compare that to the sum of the squares of the other two sides, 9 squared plus 40 squared. So 41 squared is 1,681. 9 squared is 81, and 40 squared is 1,600. Okay, so we see that 1681 equals 1681. So now we can conclude that this is a right triangle. Okay, and so last but not least, let's take a look at this last example. There we go. go. Okay, so here we have three measures. Now, because there's some radicals involved, we need to figure out approximately what these measures would be. So if you would take a calculator and take 2 times the square root of 3, you're going to get approximately 3.5, and 4 times the square root of 2 is approximately 5.6, and 3 times the square root of 5 is approximately 6.7. So now, first of all, can we make a triangle? Well, if we add 3.5 and 5.6, that's going to be bigger than 6.7. 5.6 plus 6.7 is bigger than 3.5, and if we add the first and the third, that's bigger than the middle measure. So these can definitely make a triangle. So now let's see what kind of a triangle we're looking at. So I'm going to take the biggest of the three measures, which would be 3 times the square root of 5. So I'm going to take 3 times the square root of 5, and I'm going to square that and compare that to the sum of the squares of the other two sides. So that would be 2 times the square root of 3 squared and 4 times the square root of 2 squared. Okay, so now when we square 3 times the square root of 5, we're going to take 3 times 3 and the square root of 5 times the square root of 5. So 3 times 3 is going to give us 9. If I take the square root of 5 and square it, that square is going to undo this square root. So the square root of 5 squared is just 5. Okay? Over here, let's see, 2 times the square root of 3 squared would give me 4 times 3, and 4 times the square root of 2 squared will give me 4 times 2. So we have 45 compared to 12 plus, oops, I'm sorry, I goofed up. 4 squared is not 4. 4 squared, you probably caught this. This should be 16. Sorry about that. So when I took 4 times the square root of 2 squared, 4 times 4 is 16. Square root of 2 times the square root of 2 is 2. And 16 times 2 is 32. So let's compare 45 to the sum. 12 and 32 is 44. Now, since 44 is bigger than, since 45 is bigger than 44, in other words, the square of the biggest side is greater than the sum of the squares of the other two sides, we know then that this is another obtuse triangle. Okay, all right, so in class we'll be doing some more examples and some practice problems, and if you have any questions, be sure and ask me in class.